the one for today.
That's weird. Well, I apologize for that, and for so many other things too. I'm still trying to get over this crazy thing that happens whenever you fly. It seems. I mean, it's just dangerous in the sky. Not the flying part, the getting sick part. But anyway, I'm going to be better, I think. Taking one day off today from TV, and I'll be back there tomorrow. All right, so here we are. Let's see, who do we have? We have Austin, Art. Let me go ahead and put you down. And Amir and Christopher and Travis and Mitchell. That's great. We got a lot of people here. So welcome to AER 110, the weather block. And we're going to be learning a lot about weather here starting today. So let's get right into it. And by the way, you can jump in at any time. Can you all hear me? I assume you can. I know Barbara can, so I assume everybody else can too. So just feel free to just jump in at any time if you have anything to say about anything. All right. Yes, Daniel. Oh, did you say?
Sorry, I was just going to say I can hear you just fine.
Oh, good. Daniel, where are you? Are you in Oxnard or Bakersfield or San Diego? Where?
I'm in Bakersfield.
Bakersfield. Okay, very, very good. All right. Well, welcome to intermediate weather concepts. Let's get back to this. All right, so there's a little bit of a problem with the normal satellite imagery that I use, which is this one right here. Something happened, and it is not. It is just now fixed. So this is all last night, and it doesn't have any political boundaries in here. But here's California right about here. You can see just the last couple of frames. Does it have any satellite imagery? So we're not going to use that. Instead, we're going to go to a different one. There are lots of different satellite vendors, and this shows where we are right here. We can kind of zoom in. This is visible satellite data, and you can see we do have some clouds that are kind of abutting up against the east side of the San Joaquin Valley. There's a little bit of cloudiness, mainly inland down here from Los Angeles all the way down to San Diego. But one thing I'm interested in is what's going to happen today in the middle of the country, because there's going to probably be a significant severe storm outbreak. Here is the, let's go right to the, there it is. Okay, so we're looking at the day one convective outlook, and it's looking pretty significant for a lot of the country. So everything that you see in just this kind of mint green right here, that is just the chance for thunderstorms. Once we get into the darker green, now we're talking about the potential for severe thunderstorm. This is a marginal risk is what that means. In fact, you can see the different flavors down here. Then we go slight and then enhanced. And so you can see the enhanced, which is the highest level right now for portions of Kansas and Nebraska. You don't have a moderate or high risk, but we'll see what happens. Also, there's another risk over here in the Washington, D.C. and Chesapeake Bay area. Does somebody have something to say? Sounds like somebody wanted to say something, but maybe not. Okay, so we'll be watching all of that later on today. Here is what a computer model says that the weather will be like over our area. We can go ahead and take a look at this. So here you can see California. And what we'll do is we're going to go into time, into the future. And the time is right here in the upper left-hand corner. So that is Tuesday at 18Z. I assume, but I'm not sure, that everybody knows Z time. If you don't know Z time, we'll go to 00Z right here. And 00Z means midnight at 0 degrees longitude. That's Greenwich Mean Time. And we are 7 hours away from that. We are actually 7 hours earlier than that. And so when it's midnight there, it is only 5 p.m. the previous day here. So that's 7 hours. But everything in aviation, everything in weather is all based on Z time because when you're traveling from one time zone to the other, you really need one time zone to refer to. So I will often refer to Z time. So here's, this will be tonight. Actually, this will be tomorrow night at 00Z. And it doesn't really show a whole lot going on. This particular map shows.
Yeah, like 2:30 adolescent.
What was that?
Come in early, get away from the kids and the wife and the
I
dogs.
think somebody's on.
Work done.
That's what I do. Like, what's the?
Okay.
Somebody
Right
is
now they're
muted
doing
that isn't muted.
which is kind of helpful. They're doing like a meets on weather. So
Let's see.
usually I'm
Somebody's
working on
muted that isn't muted. That needs to be muted.
It looks like
Austin.
it's Austin. It looks like it's Austin.
Austin? You
Hello,
need to mute
Austin.
yourself.
It's part of their this class.
You need to mute
Austin,
yourself.
can you hear me?
They're allowing
Austin,
you
can you
to-
hear me?
No.
Hello,
Discussion.
Austin. Go ahead and.
Everybody wants to write like a 2 to 5 page APA paper. Like
I feel like
Turn on
I'm
the phone.
eavesdropping on somebody, and they don't know.
He will
Wow.
learn quickly,
I hope.
especially since he's on the recording.
you got fight today?
That's right. Yeah. Austin, can you hear me? Hello, Austin. Are you there?
Yes, sir.
Mic test. Okay,
You're-
so you need to mute when you're talking with your friends there because it was going out. It's all being recorded too. Okay. Yeah.
Do
Okay.
you still hear me, sir?
I can hear you. Yeah. Is that that's Austin, right?
Speaking.
Okay.
I
Yeah.
don't know how to mute.
You don't know how to
Uh,
mute. Well, there's
all
there. You found it. All right. Very
Found
good.
it. Good.
Very good. Thank you. All right, we'll get back to what we were talking about here. So here we're looking at the weather map, and it shows these little lines right here. These are isobars. That is the pressure, the sea level pressure. And as we go into the future now, we're just going to go into the future, and you can see that the pressure doesn't really change a whole lot. Whenever the isobars get very close to each other, like they are here, it generally means a lot of wind. What I'm going to do now is I'm going to zoom this out to just kind of the national scale here, and we can see what's really happening across the entire country because there is a lot going on. So here we go. Now, wherever you see green, that's precipitation. And if you see yellow and orange, that's heavy precipitation. If you're looking at blue, like this here and up here in Canada, that's snow. And so we're going to go into the future here, and you can see there's a pretty big low pressure system over Nebraska. It's a 985 low. That means that the central pressure of that low pressure system is 985 millibars, which is a pretty deep low pressure system. And here it is springtime, so we're probably going to have severe weather with that. Let's see what happens into the future. It begins to go up. Now it's up to 990. And whenever a low pressure system is getting not as low, it's called filling. So this is beginning to fill. If it is getting a lower pressure, that's called deepening. And so low pressure systems and high pressure systems can change. And of course, they always do. Now we're going to take a look at what's coming. So here we have a big area of cold air up here, and the time is right here. Here's 06Z on Thursday. That is the 66-hour forecast from now. And you can see this area of very cold air, very dense cold air coming down. Let's see what happens. It's going to slosh all the way down into Colorado, Kansas, the Texas Panhandle. You can see a very, very tight pressure gradient. That means that the pressure changes very quickly. We're going from a 1012 to a 1016 to a 1024 to a 1030. So the pressure is getting much higher, and this high pressure is pushing to the south. So this is going to be like an Arctic blast. And as we go into Friday, you can see a line of thunderstorms is developing here in Texas and Oklahoma along that front. And so behind it, way up here in Canada, there's some snow, but this is all a pretty severe storm situation. So that then continues off to the east. We continue to see more cold air sloshing into much of the east. And I'll also draw your attention to these little dotted blue lines or red lines here that have numbers. Those are called thickness lines. In fact, it says thickness right up here. And that's basically temperature. So the lower that number, the colder the air mass is. And there's a magic line, and that is the 540 line, which is generally considered the rain snow line. So it's not always exact, but it's close. And so if the thickness line here is higher than 540, like 558 or 564, that generally means it's going to be rain. But if it is lower than 540, then it's generally snow. And here in these higher elevations, it's turning out to be snow, even with slightly above 540. So anyway, we have two lines here. We have the pressure lines and we have the thickness lines. And then on top of that, we have precipitation. So it looks like a lot of bad weather down in Texas there. Of course, this is way out there. This is a week from Sunday. And then let's see, we continue to see some low pressure systems across the country, across the north. And this particular suite of forecast goes all the way out to 384 hours. You can see right there that F384 means 384 hours into the future, which is 16 and a half days, which is way, way, way up there. Let's go all the way back to the beginning. We're going all the way back to the beginning now. Okay. And so this is, let's see, right? Well, it doesn't actually show the 0 hour. The 0 hour is 12Z. And so this is considered the 12Z. In fact, it says it over here. This is the 12Z initialization. So a computer model is redone 4 times a day, every 6 hours at 00Z, 06Z, 12Z, and 18Z. So every 6 hours is a whole new model, which goes 16 and a half days into the future. But this is just one of many different models. This is the American model. There's also a thing called the European model. Here's the European model, which looks at the same geography. It gives you isobars and pressure and thickness and everything else. They all do pretty much the same thing, but they're slightly different. And sometimes they are in agreements, and sometimes they're not. And so you have to know which models are best. Like this one, this is the European model. It shows some pretty significant thunderstorms down here in Texas right here on Sunday at 3Z. So let's just see. I'm just curious to know. All right, so we'll just, all right. Now let me see what the American model says about the same time. So we'll go to that. And the American model does have some thunderstorms down here. Let's go to a different model. We're going to go to the Canadian model now, see what it says. And the Canadian model, it has some thunderstorms down here, maybe, but it doesn't look quite as dramatic. We'll go to one other. Let's go to the German model, the icon model. So as you can see, there are all of these different countries that have sophisticated weather computer models that look at the data and forecast based on equations that we know how the atmosphere works. And they're all a little bit different. It's a lot like different chefs. Now, I've never thought about that, and I'm just coming up with it right now off the top of my head, but it's a lot like you go to one restaurant, or you can go to Jack in the Box, and maybe you like Jack in the Box. Maybe that is good for you, but or you might want to go to get your Chateaubriand at some fancy restaurant. I don't know, but whatever it is, it's like different chefs that have a slightly different idea of what the atmosphere will be. So here is that, and let's see. And we have so many different models here. We have too many models, I think. There are some regional models. And let me show you that. So here's a regional model. I won't get into too much detail here. We won't get into the weeds. There'll be a time to get into the weeds, and it's not now. But this just shows you. This is a model which is it's called the NAM, the North American Mesoscale model, and it is a model that is very high resolution, and you can see here we have snow to the north and rain down here and low pressure systems and everything that we saw before, but the domain is only North America. The other models that you saw are global. That means that they have grid points, so that you can look anywhere in the world to see what you want with these. For example, here's the global forecast, and we can go, let's see, where can we go? Let's go to, let's find where we want to go. We'll go continental. So here's the North Pacific, for example. And so we can look at the weather across the North Pacific. Here's Alaska over here, here's Japan over here. And so we're looking at all of the weather all across the North Pacific, or we can find some other place. Let's go to Australia. So we're going to go to Australia now. And why? It's because this is a global model. It has grid points, and it can tell what the weather's going to be like everywhere. You can see down here in Australia, and you can see Australia right here. We have low pressure systems and high pressure systems, and they go the other way down there. In fact, low pressure systems here, they spin clockwise. This is spinning clockwise. Of course, you know that in the northern hemisphere, low pressure systems spin counterclockwise. But anyway, the point is you can go anywhere in the world. Here's Africa, here's South America. Let's go to South America, see what's happening there. Of course, in South America now it's autumn, and so things are getting colder down there. So here you can see a low pressure system pushing into southern Chile right there, and a lot of thunderstorm activity across the Amazon. Okay, enough of that. Go back to
So-
our situation. Yes.
So I do have a question, Miles. Isn't one of the forecasting techniques to see how the various models align with each other for a level of confidence?
Yes. In fact, there is one particular model called. In fact, let me go back and find it here. It is called the National Blend of Models, and that takes all of the models and weighs them and shakes them out and comes up with a kind of an integrated average, basically. So let's look at that. I'm glad you brought that up. So here is. Let's go to this. We'll go here. And we can go over and look at the NWS blend of models. And so let's find something that's useful here. Let's see. Here's severe weather. We'll look at severe weather. So let's see what it says here. So this is the blend of models, which takes 35 different models. And I'm talking about all the models that we just talked about. You know, the German model, there's the Japanese model, JAMA. There's a Canadian model, and then there's a whole slew of models from the United States, including the naval model. There's an Air Force model, and so it takes all of that. And here you can see it's talking about severe storm parameters. This specifically is CAPE, and we can come down here. Let's go back here, and we can find a specific spot, and I can put my cursor right there. And that is the CAPE. That is basically a kind of instability. So 2,800 joules per kilogram, that's a lot of upward potential motion. And that is for today, in fact. And that's the blend of models. But yeah, generally, whenever you are looking at your situation, let's say you're flying from here to there in California and you need to know what the weather's going to be like, you might want to check several different models. And when you go on ForeFlight, you can look at the TAF or you can look at MOS, which is the model output statistics. In fact, we've done that before. And yeah, if all of the models are pretty much saying the same thing, then you have a higher level of confidence. Is that what you were talking about?
Yep.
All right. So let's take a look at the weather here. We're going to go ahead and take a look at. Let's see. Let's look at this first. So here's a weather map of the area, and we'll get into the specifics on how to read these weather maps. But this is here's Bakersfield up here. The temperature is always in the upper left. The dew point is always in the lower left. And the pressure, in this case, it's the altimeter setting. The 021 means 3021. And then we have 5,500. It looks like it's overcast. And if we want, we can just click on it right there. Yeah, we have pretty high pressure right now. I don't know why that is. Anyway, yeah, here's the weather observation. Winds 200 at 4. Visibility is 10 statute miles. Few clouds at 2,600. Scattered at 5,000. Overcast 5,500. Temperature 14, dew point 8 or 08. And the altimeter 3021. And there you go. So there's that. Then down here in, let's see if we can get Oxnard. There it is. There's Oxnard right there. Clear skies. Now, of course, that's clear below 12,000. And light winds. It looks pretty nice. Let's see if we go down here to San Diego. We'll go here to Gillespie Field. Come on, zoom into it there. Okay, Montgomery Field, I should say. Sorry. And let's see, 3,200 broken. So it is. There's some clouds there, but the winds are pretty light. In fact, the weather's not bad. And we're going to go over here to. Let's see. We'll go over here to Falcon, and looks like it's clear there too. So as we look at the weather observations, we can go back several hours here. This is all on aviationweather.gov. That is your go-to from the horse's mouth site to get weather information. We're going to go ahead and look at all of this and check out the TAF while we're at it. All right. So right now, This is the last, I think, what was it, 12 hours? Did I say 12 hours? Last 12 hours. Last 12 hours of observations from KBFL. So we just read this one a moment ago. Here's the forecast, which is terribly unrepresentative. I don't like to ever badmouth the National Weather Service, but that's just a horrible forecast. 20,000 scattered, and here it is, 5,500 overcast. They have, and that's the current forecast from just last hour. They should know better. And in fact, not only that, but we were actually 2,600 broken right there. What are they doing? There should at least be a temporary group. But anyway, enough of that. I don't mean to criticize the National Weather Service, but that's a horrible forecast. Anyway, variable winds, VFR is what they're saying. And it has to change like 2 flight categories before they'll amend it. They need to change their amendment criteria. But anyway, no more ranting from me. Here's Oxnard, clear skies, and their forecast is pretty much clear. As you can see right there. We'll get into the details on how to read these TAFs if you haven't already done that. San Diego, there are some clouds there at 3,500 feet. And what do they have here for the forecast? It looks like 3,500 broken. That is the ceiling. The ceiling is the lowest broken or overcast layer. And then looks like it's pretty much VFR after that, beginning here at 19Z. So with this forecast, let's just take San Diego as an example. So here's the San Diego forecast, the TAF. And so what that means is KSAN, that is the location. The 15, 17, 20Z that you see here is the date time group that the forecast is sent. It is somebody pushes a button and the forecast is out. And the date time group means it's the day of the month, which is the 15th. And then 1720 Zulu is the specific time. That would be 10:20 local time. All right, so then we have the 15:18 to 16:24. This is the valid time of the forecast right there. The valid time, it begins on the 15th at 18Z. It's just to the nearest hour. We don't have minutes on there. And then it ends at the 16th at 24Z. And this is a special circumstance. Normally, you would call that 1700Z. But whenever there's a period, a length of time, and there's a beginning and an end, if the end just happens to be 00Z, then it's called 24Z. It's the same thing as the 17th 00Z. All right, so this is then not a 24-hour, but a 30-hour forecast. So here's the winds. The winds 290 at 6 knots. Here is the visibility, more than 6 miles, statute miles. We have scattered clouds at 2,500 feet, which means 3 to 4/8 of the sky covered with clouds. And then we have broken clouds, which is a ceiling because it is more than half the sky. That is at 3,500 feet. And that means 5 to 7/8 of the sky. And then that's the forecast. And as long as we don't change it, we're going to change it right here. So this is the first change line, which is like literally the next hour. So here, this means from the 15th at 1900Z, and it does have it to the nearest minute. So at 19Z, now the winds are going to be 300 degrees at 10 knots, good visibility, few at 2,500 feet, and now scattered at 3,500 feet. So what they're saying is that they're going to lose the ceiling at 19Z. So let's see, here it is 19Z, and they haven't lost the ceiling yet. Pardon me for the cough. Good thing this is not residential. Nobody's going to get sick from me. All right, so then the next thing is, here's the next line. This is a 3Z on the 16th. The winds go variable at 4, good visibility, and few clouds at 1,500. But that's leading up to those few clouds at 1,500 becoming a ceiling. That happens right there. So at 9Z, that is the 16th of April at 09Z, winds will be variable, visibility good, but there's a ceiling at 1,500 feet. That's called marginal VFR. And there are certain rules that you need to know about marginal VFR as opposed to VFR. I guess it's a kind of VFR. It's not really good VFR, but it's marginal VFR. We'll call it VFR. Okay. If it goes below 1,000 feet, if the ceiling goes below 1,000 feet, that's not VFR at all anymore. We're going to call that IFR. And that means instrument flight rules. By the way, VFR means visual flight rules. I assume you knew that. So yeah, so we're going to not have a ceiling then at 16Z tomorrow, which is a little bit different from today. Let's see. Yeah, so not as much cloud cover. The cloud cover goes away at 16Z. And then finally at 19Z, they're just going to see a northwest wind of 10 and few clouds at 20,000 feet. And here's Phoenix. Phoenix has a little bit of a gust quotient right now. And there are some clouds, a few at 6,000, few at 11,000, and few at 23,000, and few at 27,000. Man, they are really getting specific here with their clouds. So that's good. I like to see that. I like precision in weather observations. So we got a lot of clouds. We got some low clouds, some middle clouds, and a couple of high clouds there. Temperature 22, dew point 0, and altimeter 2 niner. And everything looks good here. Although they're just saying clear skies, which they should have some clouds in there, because I know that there are some clouds because I'm seeing them right. Well, not much. Okay, here's Arizona. Yeah, there are some clouds right there, just a few. All right, so that is that. Let's take a quick look here at the models. We're going to look at this first. So here is this is the model data from the GFS. That is the American model. Here's Bakersfield, GFS, MOS. MOS, remember this. Remember, this stands for Model Output Statistics. So these are the statistics you need to know from the model output. Here are hours right here, every 3 hours. And you can see the day right above it. So this gives the low temperature, then the high temperature right after that. Stop. And then the low temperature and the high temperature for the next day. This gives the cloud conditions right there. And you can see broken clouds initially, but then it goes clear after that. And this gives the wind direction and the wind speed right there for each of those 3 hour periods. And once again, here's the times right up here. Let's see. And then this is the extended forecast. This is Tuesday through Wednesday through next Monday. And it'll give the low and the high temperature, low and high, low and high, low and high. So it says that Bakersfield will be up to 84 degrees by Tuesday. Big change from yet. We had a high of only 59 yesterday. We almost broke a low maximum record. Not quite, but it looks like once we get past tomorrow, we'll be in the 80s every day. And the cloud cover will not be an issue. There'll be some clouds, PC for partly cloudy there on Friday. Now, we talked about the national blend of models, so let's take a look at the national blend of models for Bakersfield and for, we'll say, Oxnard. Only because I know that Barbara is near Oxnard. So here we go. So here, we'll go to Oxnard first then. So here we go. Here's Oxnard. And this is that NBM. Remember that? This is the one that takes all the different models and weighs them and shakes them up and comes up with an output. So here we got the temperatures. This is the maximum temperature right here. So high today of about 62, and then 50 tonight, 69 tomorrow, 69 the next day. It looks like it's going to be the same. The one thing that is different here is it gives sky coverage in percentage. So 14%, that's not a whole lot. And here, single digit percentage is basically clear. We do have some cloud. Well, we never really get into a ceiling until we get above 50%, which is right there. So, and that won't be until, let's see, so today's Monday, so this is Tuesday, so that'll be Wednesday, I guess. And once we do have some clouds, it gives the SIG. Now, SIG does not mean cigarette, it means ceiling. And here you can see a ceiling of 3,900 and 4,400 and 10,000 feet and 900 at the very end. And the time, by the way, as was the case before, is right up here. Here's every 3 hours. So that's that. And here's Bakersfield. It's all the same. And this is something that you can do. It's just right there. Anybody can do this. Let me find one more thing. I'm going to get the extended version here. Here's the extended version. Now we're going to go into the future. And let's see. And so this says 86 degrees. Now, I should caution you, it says Friday at 00Z up here, but Friday at 00Z is Thursday afternoon. So that 86 degrees is not for Friday, it's for Thursday. Just got to kind of remember that. But it looks very consistent from there on. It looks like mid 80s every day and overnight lows in the 50s. So we're going to shake this kind of wet pattern that we've been in. In fact, the rain that came over the weekend was a little bit unexpected. As you know, I was in, maybe you don't know, I went to Texas to see the eclipse, and I had already sent out a forecast. I do a forecast for agriculture every Monday, and I had to amend that forecast when I came back when it looked like we were going to see this a cold storm, and we did. We had a good amount of rain yesterday and the day before. Here's Oxnard. Looks like you two are going to be pretty consistent there. Looks like not much in the way of any cloud cover, so it looks good all the way around. All right, so there you go. Are there any questions about our weather, which is going to be coming up? Look, it's not looking bad.
Actually,
yes,
the weather yesterday was quite interesting because it was also quite convective.
Yes,
we kept getting pretty
Let me
strong
see
rain
if there was-
showers and relatively low icing levels.
let's see. Yesterday there were no severe reports of anything, so let's see if there's been any today. Nah. And then after, by the way, when I was in Texas, not only did we have the eclipse, but we had some severe weather. Let's go back. Yeah, this is the 9th. That was the next day, and there were like tornadoes and some pretty big hail right around where we were. So it made for a big deal. In fact, I don't know. Let me see here. Do we have anybody else that's not here? Here, I can show you if you care. I can show you my. Let me stop sharing here, and then let me start this again. This and this and this and this. All right. So I can show you the little eclipse piece. Here it is.
Going. Let's start.
The celestial event of the season has begun. We're here in the Texas Hill Country right now, where the moon is just about to completely eclipse the sun. It is getting darker by the instant. The wind is picking up. And take a look at the sun if you possibly can. It's about to completely go out. Looking at the last little sliver of it beginning to move on out. It is getting viscerally darker right here. So dark that there's going to be pitch black here any second. A lot of people have been waiting for this moment, and it is taking place. It should be completely eclipsed for about 4.5 minutes, coming up any second. Now it's getting so dark, everybody is noticing it. It is a wonderful experience for people to come together, not only here, but millions of people throughout the United States right now. This won't happen again for another 20 years. You can hear the delight from the crowd right now. And take a quick look as it goes away. And there it is right up there. And now we are eclipsed. And there's the moment. Totally eclipsed. It's a wonderful moment for everybody. From Grapetown, Texas, near Fredericksburg, I'm Miles Musio, Eyewitness News.
All right. I just thought you'd like to see that. I don't know. Let's do this. Let me do this. And this. This. And this. All right. Now we're going to talk about today's topic. Let's see. All right. Is everybody still there? Can you hear me?
Yep.
Just want to make sure. Oh.
Yep.
Oh, okay, good. So let's do this. This. All right. So welcome everybody. This is Intermediate Aviation Concepts, and this is the weather block of AER 110 that you've been enjoying with Barbara Fulkin. And so we're going to be doing this for the next 4 weeks. Today, we're going to be talking about the motion and meteors. Stability and energy comes up on Wednesday. And again, if you ever have any questions about anything, just blurt in. Barbara, do you have a question?
Yeah, I have two things. I'm going to change from my desktop to my phone because I have to go to the airport. So I'll be back on. And I have something that I wanted to talk to you about. I participated in a research study here, I don't know how many months ago, from, I don't forget, University of Illinois, on augmented reality for weather, and they want some inputs on their tool. So I think I'd like to get you involved in that.
Oh, I'd love to, yeah. Augmented
Okay.
reality. That sounds almost
Augmented
like AI.
Not
It's
AI,
A-
just augmented AR.
It's
So
AR.
I will
Okay.
send that information on to you and we can talk about it later.
Okay, great. All right. Then let's see. We're going to see if this works. There's synoptic weather will be next Monday, and then forensic aviation weather comes up on Wednesday, the 24th. Then we're going to talk about an introduction to weather models. That'll be coming up 2 weeks from today. Thunderstorms, and then general weather and hazards after that. And then the review and exam comes up on the 8th. So motion and meteors, stability and energy, et cetera, et cetera. And we have a mid-block quiz and a final exam. Your passing grade will be 60%. This is me, by the way, if you don't know who I am. I'm Miles Musio. I also do TV. Been doing it for a long, I've been a meteorologist for over 50 years. Like, here's a picture of me with Gene Cernan, the last man to walk on the moon. I did lunar landing training vehicle weather support. This was back in 1972. And this thing in the background is the lunar lander. And I sent up weather balloons to get the precise wind as they were using that to simulate a landing on the moon. So that was in Houston, where I met my sweet wife, by the way. Anyway, so that's that. And I've been doing a TV since 1980, so that's just a long time. So anyway, if you have any questions about anything, I'm your weather resource, and my name is Miles, and milesm@calaero.edu. And we're going to do a daily weather briefing every day. And that's what I looked like many years ago. Oh, geez, how time flies. But anyway, we're going to be doing that. And so that's one of the neat things about this particular course. We are always looking at the weather as it changes, because the weather is different every day. It's not the same. And if it was just a canned course, then you wouldn't get the benefit of seeing how the weather changes and the resources to use. Okay, now that we've done all that, and I've done my last cough of the day, we're going to move on to today, motion and meteors. So here's the Earth. It's a great place to live, an ideal place, in fact. But you'll notice a couple of things. This is a great shot. I believe this is from Apollo 17, the same Apollo mission that I worked on. You can see a lot of it is ocean. All of this is ocean. That's called the hydrosphere, and that is water. That's about 70%. Then we have this other thing called the lithosphere, which is the dry land, and that is about 30%, which is good to know. That is roughly the same percentage of water that you have in your body. You are 70% water, just like the Earth's surface is 70% water. And so a lot of that water, there's so much of it, of course, evaporates. And remember that of the land, more than double the area of land is water. So a lot of that, the moisture can find its way over land, and then it'll precipitate, and we can have life. Also, the atmosphere is composed mainly of nitrogen. You can see the numbers here. 78% nitrogen. That's a lot of nitrogen. And that is sort of the venue in which we have the active ingredient for metabolism, and that is oxygen, which is about 21%. So 21% is right here, and that is what you need for, I say, metabolism. That is how your cells actually live. Blood has hemoglobin in it, which takes the oxygen that you breathe in from the atmosphere and then disperses it throughout all of the cells of your body. But again, it's not the main part. The main part of the atmosphere is all this, which is nitrogen. It's not exactly the same ratio of the hydrosphere to the lithosphere, but it's roughly the same. So there's a venue, and then there's the active ingredients. Then we have this very small part down here. This is just the trace elements. We have carbon dioxide, neon, helium, methane, and krypton. Yes, and krypton is a gas, by the way. It's a noble gas. And it's not something that you have, that I guess, yeah, kryptonite. That's something that Superman has to worry about. But here we have carbon dioxide, which is about 0.04%. But carbon dioxide is a very important constituent in the photosynthesis. So the plants, of which there's a lot more plant life than there is animal life, and there's a lot of animal life when you include all of the one-celled animals and all the insects and bugs and all that stuff. There's a lot of that, but there's a lot more vegetation. So the vegetation uses carbon dioxide from the atmosphere together with water and light, ultraviolet light. And so through the process of photosynthesis, it lives. And the byproduct of all that is oxygen, which, surprise, animals need. Not just people, but all animals need oxygen. So there is this symbiosis. Symbiosis. That means that there are two different entities that kind of need each other. So, and those are plants and animals, and we need each other through oxygen and carbon dioxide. And carbon dioxide is a greenhouse gas, and it's a good thing that we have it, because without it and the other greenhouse gases, there would be no life on Earth, because we would be too cold. So here you can see we start off with several different subspheres of the atmosphere. So the atmosphere is the whole, here it is, this is the atmosphere, the little thin blue blanket that William Shatner called it when he took a little ride in Blue Origin. He went up and he was officially in outer space. And then he looked up and he saw nothing but blackness. And then he saw the little blue blanket down here, and that allows life on Earth. Anyway, so in the atmosphere, we have the troposphere, then the stratosphere above that, and in which case the temperature rises. You know, who would have guessed that? And then we get up to the mesosphere, and the temperature gets very cold again. And then we have the thermosphere, and temperature gets very warm again. So here's the way it works. There is sunlight from this star, which is nearby, called the sun, and it heats the Earth with shortwave energy. Shortwave. That means that the electromagnetic waves are short. It warms the Earth, and then the Earth will re-radiate back into outer space at long waves. Long waves. Long waves. That's the difference. Long waves. Now, those long waves that are being re-radiated out into outer space, this is called the black body phenomena, because whatever has heat in it, like this coffee cup right here has heat in it, it is always radiating that heat out, trying to achieve some sort of balance with the air in the room or something. But anyway, something is always re-radiating heat out until it gets to a balance. So that heat coming up from the Earth, the pre-warmed Earth, it was warmed, remember, it was warmed by the shortwave radiation from the sun. It is now re-radiating that out. And that re-radiation will then resonate with carbon dioxide molecules. This is the oxygen in the middle, and that's the carbon. The carbon, that's the carbon in the middle. That's the oxygen on either side, sorry. So we have that. And at certain wavelengths, certain long wavelengths, it'll cause the molecules to kind of move. And not only that, but also water vapor and methane. These are also greenhouse gases. These are invisible gases that resonate with long wave radiation coming up from the Earth, radiating back out into outer space. And so that's why it is warmer than it would otherwise be. So here, hot objects emit short waves. Cool objects emit longer wavelengths. So there you can see some short wavelengths coming in from the fire right there, and the dog loves it. But it's quite a bit different here. For the sun's photosphere is about 6,000 degrees Kelvin. Earth is about 288 degrees Kelvin, which, by the way, would be it would be even cooler were it not for the greenhouse gases. In fact, here's the sun over here, and here's the Earth over here. This is about 93 million miles. And at that particular distance, the temperature should be cooler. It should be, let's see, it should be about 0 degrees Fahrenheit, which would be minus 18 degrees Celsius. That is what the temperature should be, which would be quite a bit cooler. But because of the greenhouse gas, this then is up now to 59 degrees, and this is up to 15 degrees Fahrenheit. So we are, in essence, 33 degrees warmer than we would normally be due to our distance from the sun. And that is because of the greenhouse effect, which is a great thing. All right, so here you can see convection, and you know what convection is. This is upward motion in the atmosphere. That's one way that you can transfer a heat. You can do it vertically like that. Here's radiation down here. It's coming of the shortwave radiation. And then the conduction is the transfer of heat through solid objects. So short wave down here, long wave up here. All right, so we're just talking about the difference between short waves and long waves. Now, here's a very important graphic for you to look at. By the way, I'm going to be sending out to everybody via email all of the lecture slides. I'll do the first half now, and then once we get past the 2 weeks, I'll give you the second half of the course. So you can look at these things at your leisure. So here, down at the bottom, you can see the wavelengths. So here is 1 micron. 1 micron, that's a mu, equals 10 to the minus 6 meters. That's pretty small, 1 micron. So the electromagnetic energy at 1 micron is right about here, and that's a little bit more than visible energy. Once we go this direction, this is short wave. And here's 0.1 microns. We go the other direction, this is long wave. Here's 10 and 100 microns. So the thing to look at is oxygen, carbon dioxide, and water, and how there are resonating points. So carbon dioxide will absorb the energy at these specific wavelengths, 2.7, 4.3, and 15 microns. Okay? So that means that at those specific wavelengths of long wave radiation coming up from the ground, they are what's known as thermogenic. Thermogenic. That means that they are creating heat because they are resonating with the energy coming up from the ground. And it's a lot like taking your hands and brushing them together really, really hard, and you can feel the heat. It's called kinetic heat. It's just molecules brushing up against each other very fast. So carbon dioxide creates heat at this wavelength, and this wavelength. However, this is something interesting here. We have oxygen, which does the same thing, oxygen and ozone. But you'll notice for the most part, it's way up here in the short wave range. There's one little peak over here at 9 microns. But oxygen will absorb shortwave radiation in the ozone layer at the base of the stratosphere. And so it's creating heat in the stratosphere. And that is why temperature stops falling and it begins to go up in the stratosphere. It's because oxygen is absorbing and resonating with shortwave radiation from the sun. And that's why we have that whole interesting thing about temperature gets to what's known as the tropopause, which is the point at which the temperature stops going down with height, and then it begins to go up a little bit. Finally, we have another invisible gas, and that's water vapor. And you will notice that there are multiple points here where water vapor will absorb energy and will become thermogenic. And you'll also notice that water vapor is much more impactful as a greenhouse gas than carbon dioxide is. Carbon dioxide is somewhat, it's there, but it's not. And there's generally a lot more water vapor in the atmosphere than there is carbon dioxide. So here is the incoming radiation in, we'll say, percentage. It will say 100 units. So of those 100 units, how much is absorbed by the land? Well, it's right down here, 46%. Not even half. And all of this other stuff is kind of absorbed by clouds, or it's backscattered by the air, reflected, whatever, or reflected by the surface. So of the 100 units of solar radiation that gets to the top of the atmosphere, not even half of it gets to the ground. And then of this 46, this is the outgoing. So let's see, we have 15 plus 7 is 22 plus 24 is 46. So yes, okay, so 46 in, 46 out. And there's latent heat transfer, there's sensible heat transfer, there's emission by clouds. And this 6% right here, that is the greenhouse thermogenic part. So 6% of all of the heat coming into the top of the atmosphere initially is part of the greenhouse warming that we have. And that's just the way that works. So there's differential heating, and so we have all of this heat coming in from the sun, but there are different types of land and ocean, different albedos, and because of albedo basically is how much reflection or how much absorption a piece of land will do. Like really dark areas will absorb a lot more. They'll get hot. Other areas like ice fields and ice caps, they will reflect. And so there's just simply a difference in that. And because of the differences, we have high pressure systems and low pressure systems. Where it gets really hot, all the air goes up. And when the air rises, because warmer air is less dense, when it rises, then all of a sudden there's no air because the air just went up. And so there's a low pressure system. And so that air, the vacuum has to be filled in from high pressure systems. And so that is where we get wind. Wind is caused by differential heating of the ground. We're going to talk now a little bit about the hydrologic cycle. This is really important here because, as you know, 70% of the Earth's surface is water. Only 30%, less than half of that coverage is land. So we got lots of water kind of floating around in the atmosphere as vapor. So here is the hydrologic cycle. We're going to start off with evaporation. You cannot say evaporation without the word vapor in it, so there it is. So that means that liquid water becomes vapor. It turns into a gas, and that the vapor can then rise into the atmosphere. It can then be transported on the winds. There can be sublimation, which is simply snow that goes directly to vapor. It doesn't pass through the liquid part. So we have three different ways of getting vapor into the atmosphere and moving it around. And then we will see the next part of this cycle, and that is the condensation. So now the vapor becomes liquid again, and it falls, and then it can fall and get transported through runoff to different areas. There's precipitation, and it could be either rain or snow. Then finally, we have the runoff and the infiltration into the ground. And then we have all the way down into the groundwater flow. That's where plants will take up the water. And in fact, I had failed to mention this initially. Transpiration. Evapotranspiration is liquid that gets into the atmosphere and becomes vapor, I should say, from leaves and trees. There's so much vegetation out there, as you know. In fact, once the leaves pop out on the trees across much of the country, eastern half of the country, during springtime, and then all of a sudden the humidity goes up, in part because of all of the water which is taken up from the groundwater flow, and then evapotranspiration, or just transpiration, actually gets into the atmosphere through all of the plants and leaves. So that's just kind of an interesting thing. So we have all that. And then, of course, all of the water gets back into the ocean, because that's where the rivers take it, into the bays and the gulfs and the oceans. And then it starts all over again. But it's all the same water, just in different forms. It's interesting to note that water is a little bit different. If you have sand and then you add this much heat to it, you will see after adding that heat that water will only go up 1 degree Celsius from 25 to 26, but the solid will go up 5 degrees from 25 to 30. And that's just to tell you that water is very conservative. It doesn't change temperature nearly as fast as land does. And that'll become an important thing to remember when we talk about different winds, local winds, for example, sea breezes and things like that, because the temperature of the lakes in the Great Lakes, for example, they change very slowly. They are warmest in September. That's like 3 months after the sun is the highest, because they very slowly warm up and then they very slowly cool off. And the Great Lakes, just using that as an example, are coolest usually in March, way after the cold, darkest time of the year. So this atmospheric water comes in 3 different states or phases, and you know this: solid, liquid, or gas. And there are other states of being, plasma, for example. We're not going to talk about that because that doesn't really apply to a water. But so here we have water vapor molecules, and this is important to know. So if you look at a cloud, here's a cloud, and so I would ask you, is that solid, liquid, or gas? And people might say, well, let's see, that looks that's gas. That's those are clouds. Those are fluffy little clouds. We're looking at water vapor. Well, the answer is that if you can see it, then it is liquid, because water vapor is invisible. It's just as invisible as oxygen and nitrogen. So this invisible water vapor will then condense into water droplets and become visible. And when that happens, it actually releases heat. It's a thing called latent heat, which I'll describe in just a moment. And then that heat causes it to rise even more. And so we get convection. And you'll see that lifted air will develop clouds, which of course is liquid water droplets. And then coming down the other side, once it begins to sink, the air will dry out. So that's the way that works. So here is just an example of vapor pressure. Okay, so let's say we have a certain atmospheric pressure. Let's just say the pressure is 10, 12 millibars. 10, 12 millibars. There might be an isobar that says 10, 12 millibars. And of course, 1,000 millibars equals 1 bar, right? 1 bar. That's where we get the word barometer from. So of the pressure in the atmosphere that you have to always know about whenever you're dealing with an altimeter setting to know what your altitude is, a certain portion of that comes from vapor. So there's a certain amount of water vapor in the atmosphere that also is extending or impinging pressure. So as the temperature gets, as the dew point in this case gets higher and higher, let's pick 70 degrees right there. So at 70-degree dew point, that means that 25 millibars of the total pressure comes just from water vapor. Here's 50 degrees. If the dew point is 50, that means that 12.3 millibars comes just from water vapor, not from oxygen and nitrogen and all that. So the higher the humidity, generally, the higher the pressure will be. So as temperature increases, there's greater water vapor pressure. And as temperature decreases, there's less availability for water as vapor. And here's a great example of that. So here we got 3 different temperatures. Here's 30 degrees, which is 86 degrees Fahrenheit. Here's 20 degrees, which is 68 degrees Fahrenheit. And here's 10 degrees, which is 50 degrees Fahrenheit. And you'll notice in these little blocks that we have a certain amount of water vapor, grams of water vapor. We have 1, 2, 3, 4, 5, 6, 7, 8 grams of water vapor, which is invisible, by the way, in this particular parcel of air at 30 degrees Celsius, 86 degrees Fahrenheit. So what we know is that there are potential grams of water vapor that vary depending upon the temperature. It's a 1-to-1 ratio. I mean, it's a direct ratio. And here, so if we have 8 grams of actual water vapor in an atmosphere that is 86 degrees Fahrenheit, which can hold 27 grams, then we determine what the humidity is by dividing how much actual water vapor is in a parcel by how much it could hold based on that temperature. In this case, 8 divided by 27 is 30%. So the relative humidity is 30%. And it's called relative humidity, you've heard the term, because it's relative to the temperature. That means that as the temperature goes down, the humidity will go up, even though you haven't added any moisture to the air. Now you can add moisture to the air and the humidity might go up, but it's relative to the temperature. That's what relative humidity means. So let's cool the atmosphere from 30 degrees to 20 degrees Celsius. Now at that temperature, you can only hold 15. That's just the way it is. So we have 8 grams, but you can only hold 15. So 8 divided by 15 is 53%. So the humidity went up, not because we added moisture, but because we cooled the air down. All right, so now we're going to cool it down again to 10 degrees. And now at 10 degrees, how much can it hold? It turns out that it's 8. So it is saturated. 8 divided by 8 is 100%. So what do you think would happen if we cooled it off again? I don't know, to say 5 degrees Celsius. What does anybody think? What would happen? What would happen? And you can just let me know. You can just unmute and tell me what you think. What would happen if the temperature got cooler than 10 degrees Celsius? Anybody?
You would have raindrops.
Yes, that's what would happen. So once you get below the temperature that you can hold that amount of water, then you will get condensation, and that is exactly right. So if the air cannot hold the water vapor, then it just will squeeze it out like a sponge. And so that's exactly what happens. So yeah, so I'm not sure how much air, how much water vapor a 5 degrees Celsius can hold, but it will condense. And then we get to this interesting thing here. And then, yes, then you'll be able to see it. And then clouds will form or fog will form. And if enough cloudiness forms, then perhaps we'll get some rain. And next thing you know, thunderstorms or maybe snow. But yeah, that is exactly what it is. So it's all based on the temperature and how many grams of water we have in the atmosphere. So here we have vapor, like we were just a moment ago, and now we're going to condense because we've gotten below the dew point. The dew point, and you'll notice we have the dew point in all the METAR observations. You know, the temperature and dew point go together like peanut butter and jelly, love and marriage. I don't want to know what the temperature is without also knowing what the dew point is, because that's you just get more information right there. So and that's also very important with density altitude. You have to know how much moisture is in the air. So when water vapor changes its chemical orientation, because vapor is just very chaotic, it's just flying around. But once it condenses, then it becomes a little bit more organized, a little bit more rigid. And what happens is that there's a thing called latent heat. And so when we condense, there is a release of latent heat into the environment. How much? 2,501 joules of energy per gram of water vapor. That is how much heat is just released into the atmosphere. So if you condense and clouds begin to form, then heat is being released. Whenever you see any cloud just develop, heat is being released. It is radiating heat. Quite often, when it's a cold night in the winter and it's clear, and all of a sudden some low clouds come in, the temperature goes up. And one of the reasons is because, well, you have radiating clouds, radiating heat. And that's why that happens. Now, the interesting thing is when you go from liquid and you freeze, which is kind of the same direction. It's the same direction. We're going from, in this case, right to left. We're going to just like condensation. When it freezes, now there is 334 joules of energy per gram of liquid water when it finally solidifies into ice, which is not nearly as much as the previous 2,501 joules. So that's interesting. Now, there are some things that are just completely counterintuitive. Let me go ahead and show you that real quick here. Let's see, we'll do this. This is counterintuitive. In other words, that means it doesn't make obvious sense. So if you go the other direction, and you've probably heard about this, so we're going to go liquid to vapor. We're going to evaporate. We have the same amount of heat, but in this case, it is going to be absorbed from the environment. So if you're taking heat from the environment as liquid evaporates into vapor, that's a cooling process because you're taking heat from the environment. So evaporation is a cooling process, which you probably knew. That's what evaporative coolers are all about. In the Central California and much of the desert Southwest, we have swamp coolers, is what they're called. And there's nothing more than just a pad that has water on it, and you blow air over it, and then it cools. It's the same thing as your body. Your body actually has pores, and when it gets hot, you start to sweat. But the sweat will then evaporate, and when that happens, it cools you off. That's why it's the same thing as licking your finger and blowing on it. It's cool. Try it, as if you didn't already know. So yeah, evaporation is a cooling process. If you are, however, in a very humid atmosphere, let's say you're in South Texas and the dew points are in the 70s, and there's already all this moisture in the atmosphere and you're sweating, there's no room in the atmosphere for your sweat. So it doesn't evaporate, you stay hot. And that is how you can be hot and humid. And it doesn't help that you're sweating. But if it's a dry desert atmosphere, it's not quite as bad because you stay a little bit cooler. Now, the thing that is counterintuitive, so this is a cooling process. If you go from solid to liquid, In other words, you're going to melt. And in that case, 334 joules of energy per gram of ice becomes liquid. Melting is, in fact, a cooling process. That's right. You heard me right. Just like evaporation is a cooling process, melting is a cooling process. Condensation is a warming process, but so is freezing. Freezing is a warming process because it adds heat. That's counterintuitive. You'd say, no, it's a freezing, it's a cooling process. No, it's not. Remember that. That's one of those counterintuitive things. Now, there's one other thing here. It's called sublimation. That is when you go from ice directly to vapor. You don't pass go and collect $200 in liquid. And that, in that particular case, 2,834 joules of energy per gram of ice is then released into the atmosphere. I'm sorry, not released. It is taken from the atmosphere. So when it sublimes and like snow becomes vapor, that is a cooling process. On the other hand, when you do the opposite, you go directly from vapor to solid, that's called deposition. That is like frost. So frost just kind of develops on a cold winter's morning on your wing or something like that, or in your mailbox or whatever it is. If frost develops, that's called deposition. And oddly enough, it's the same exchange of heat. It is 2,834 joules of energy per gram of water vapor, and that is released to the environment. So when frost is developing, it is radiating a lot of heat. And there you go. All right. Are there any questions about all that? That's some pretty important stuff to know about water. And no questions about anything? Nobody was surprised about the counterintuitive thing that melting is actually a cooling process? Okay. So now we're going to go to a cloud formation. So here, you'll notice that as we go up, and this is thousands of feet over here, generally temperature will go down 3 degrees per 1,000 feet. 3 degrees per 1,000 feet. So we'll go from 18 to 15 to 12, 9, 6, and 3. And that is called the lapse rate. That is how fast the temperature cools with height. The lapse rate. Lapse rate. Lapse rate. In this case, 3 degrees per 1,000 feet. And there's also a lapse rate for the dew point. And it is about a ½ degree per 1,000 feet. So 3, 2.5, 2, 1.5, 1.5. Okay? And of course, you can calculate the humidity based on the temperature dew point spread all the way up. So if air goes all the way up and then comes all the way down, those are the temperatures. Now, what happens if there's a little bit more humidity? We started down here with a dew point of only 3. Let's say we start with a dew point of 13, which is a whole lot more humidity. So we're going to go down 3 degrees per 1,000 feet until we get to 2,000 feet. Now from there, it's going to change because we have reached what's known as the lifting condensation level. That is the base of the clouds. In this case, it'll be 2,000 feet. The temperature and dew point are 12. The dew point was going down a ½ degree until it finally got there. So what happens now is that because of that latent heat of condensation, you remember that latent heat of condensation, because of that, which releases heat into the atmosphere when water vapor becomes liquid. Because of that, it changes the lapse rate. Now, the lapse rate, as you can see, is 2 degrees per 1,000 feet. So now we're going down to 10 and then 8 and then 6. And we get up here to 5,000 feet, and now the temperature is 6. One other important thing to remember is that the dew point can never be any higher than the temperature. So once we are 100% humidity, we're just going to stay 100% humidity all the way up to, in this case, 5,000 feet. So the temperature and dew point will be the same throughout this whole process. Now we're going to go back down from 5,000 feet. We're going to go down, but again, now we're not going to be saturated. And so we're back to the 3 degrees per 1,000 feet, 3 degrees per 1,000 feet, till we get back down to the ground. And the dew point will go up at a half degree per 1,000 feet until we get down to the ground. So now, if we start off, what did we start off as? We started off at 18 degrees with a dew point of 13 down here. We're going to go all the way up to 5,000 feet with clouds from 2,000 feet up to 5,000 feet, then come back down. And now it's warmed up and dried out. Instead of 18 and 13, it's 21 degrees and 8.5 for a dew point. The humidity, which started off at 73%, after this process is now only 45%. So that is what happens with condensation and evaporation. Hey, some pretty neat clouds. Huh? These are some lenticular clouds right there. And that's a great opportunity to explain this one more time. So we're going to be at 2,000 feet right here, and we're going to go up the mountain. We're going to start off. Let's see. We're going to start off at 15 degrees with a dew point of 10. We're going to get all the way up to, how high is this? 12,000 feet right there. Okay. By the time we get up there, the temperature is -7, the dew point is -7, but then we get the warming at 3 degrees per 1,000 feet. And when we get back down to 2,000 on the leeward side, it's called the leeward side. This is the windward side over here of a mountain. And you get on the back side or the leeward side, you'll notice that the temperature now is 23 degrees with a dew point of -2. That's a big difference. That's one of the primary reasons why there are deserts on the east side of the Cascades, the east side of the Sierra, stuff like that, because that's the leeward dry side. So here we have a low pressure system that has upward motion and that produces clouds, and high pressure systems are generally downward motion, and we have dry air. And of course, clouds also form along cold fronts. And here's a cold front. A cold front has a little bit of texture, vertical texture to it. It looks like kind of a bulldozer. You know, it's kind of got an edge to it right here. And then it slopes back as you go into the colder air. Here's a neat cloud. This is called altocumulus cavum. And you'll notice that it's a big hole in the sky. That was not created by a jet or a rocket or something like that. But you'll also notice that we have some high clouds here. These are all high clouds. And these other clouds over here are all mid-level clouds. And so what happened was that the high-level clouds formed. It was deposition. They formed out of water vapor. And then all of a sudden we had all this heat. It's something like 2,800 joules per gram of water vapor. And then that heat actually somehow burned a hole in the clouds below it, which is pretty amazing. So it's pretty neat stuff, clouds. Let's take a look at the fundamental cloud types. So there are 10 fundamental cloud types. And here they are. They come in 4 different categories. And I should also tell you that just like animals and plants, there's scientific taxonomy. In other words, if you want to know what a particular plant is, you can give the Latin name to it. Or human beings, we are Homo sapiens, for example. That is the genus and species of people. It's the same thing with clouds. They have genus and species too. But right now we're going to talk just about the genus. The plural for genus is genera. And so here we have 4 different categories, not 3. Many of you are going to say there are 3 categories, and you'll be wrong. There are 4 categories. Low clouds. These are clouds that are based below 2 kilometers or 6,500 feet. Those low clouds are stratus and stratocumulus. Stratus and stratocumulus. Stratus are just kind of horizontal layered clouds, sort of like the word stratus in Latin means just layer. And then stratocumulus, which is kind of a hybrid cloud. It's not exactly stratus, it's not exactly cumulus, it's a little bit of both. So it's kind of a layered cloud with a little bit of texture to it. Those are the 2 low clouds. And then there's another low cloud, which also extends way up into the atmosphere here. You can see it right there, extending way up. And that's called nimbostratus. And nimbostratus, the word nimbo means precipitation. So if there is a rain cloud from a deep low pressure system, it would be called nimbostratus. Then we have convective clouds, and this is a whole category by itself. This is the one that some people don't seem to remember. So convective cloud, this is the second of 4 categories. Also clouds that are based generally below 6,500 feet, and they are cumulus and cumulonimbus. So cumulus are clouds which have vertical motion. In other words, there are air currents that are causing them to kind of puff up into the sky because they are vertical currents of air. And so they look a little bit like this. If they get really tall, like a thunderstorm, they get up above the freezing level, and then you have ice in the top of the clouds, which will then cause lightning and thunder. Those are called cumulonimbus clouds. And on a METAR, it's CB. So CB, northeast, moving east. Might be something as you'd see on a METAR observation. Those are convective clouds. Next up, we have middle clouds, which are based between 2 and 7 kilometers, or between 6,500 and 23,000 feet. These are middle clouds. They have the word alto in them. Alto tells you these are middle clouds. That's what it means. It says middle cloud and then stratus. So instead of stratus in the low cloud region, this is middle clouds. So alto stratus is one, and then another is alto cumulus. And you'll find that there are basically 2 different kinds of clouds. There are 2 types of clouds, stratus and cumulus. And then there are all these iterations of that. You know, there can be stratocumulus, altocumulus, which is basically cumulus in the mid-cloud range. And then finally, we have high clouds. That is the 4th of the 4 categories. These are clouds that are above 6 kilometers or are all ice. So here we have cirrus, which means hair, a wisp of hair. We have cirrostratus and cirrocumulus, and you would expect that because there are only 2 kinds of clouds, stratus and cumulus, and all of the other versions of it. And there you go. We have 10 different fundamental cloud types. These are the genera. This is the genus. And then once you get into my next class, AER 300, we have a whole class on the various species and accessory clouds and varieties. There are many, many different kinds of clouds that are all identifiable. And the clouds speak to you. You're the pilot, and the cloud is talking to you if you are listening. So we'll get into that in AER 300. These are the fundamental clouds. And then, of course, we have weather, and there are 100 different types of weather that are observable. And we're not going to go into all of them here, but we're going to give you the categories. So here we start. This is 0, 0. This is 10. This is 20. This is 60. This is 70. This is 90 down here. This is 0, 1, 2, 3. So if you're looking at like 45, that would be, let's see, this is 40, and this is 5. So that would be this. That's 45. So that's what we're looking at right here. So the first are just no weather, just clouds are either increasing or decreasing. Next up are lithometeors. You might say, lithometeors, what is that? Well, you remember that when we talked about the hydrosphere and the lithosphere, that the lithosphere was the land portion. So when you're looking at the different types of weather, everything that appears in the sky and falls from the sky, or you can just behold, there it is in the sky, is called a meteor. Meteor. Not just the falling stars, not just the bright little meteors that you see for a moment. Those are meteors too, because there they are. But anything in the atmosphere is a meteor. Now, there are different kinds of meteors. So we have hydrometeors, and a hydrometeor, the word hydro means water. You knew that. So anything that involves water that is in the air that is falling, like rain or drizzle or snow or hail or something like that, that would be called a hydrometeor. Lithometeors are dry. These are things like smoke, haze, dust, dust devils, and things like that. And they're just as important. I mean, they're there. They can be obstructions to vision. And those are called lithometeors. And there are certain types of lithometeors that can blow, like blowing dust, blowing sand. Those are lithometeors. By the way, we have others too. We have electrometeors, and I'm sure you can probably figure out what that means. Does anybody want to tell me or give me an example of an electrometeor? Anybody at all? An electrometeor, what would that be? Don't be shy. Nobody knows what an electrometeor is. It's in the sky. You have to have
Lightning.
this. Lightning is correct. That's exactly right. It is a movement of electrons, and it is very, very bright, and it causes thunder. In fact, thunder is the result of lightning. So let me just show you this. So here we have a cloud. Here's the ground down here. And if the top of the cloud gets to a point where it's below freezing and you have ice in the top of the cloud. You have to have ice in the top of the cloud. Then what happens is that we have those ice pellets, they're not ice pellets, they're ice platelets, and they brush against each other and they rip off electrons. And so the top of the cloud gets very positively charged. The bottom of the cloud is negatively charged because of that. And then the ground, which is normally negatively charged, actually becomes positively charged as a shadow beneath the negatively charged base of the cloud. Then all of a sudden, at some point, it just reaches a titration point, and bingo, it needs to balance and equalize. And so we have this flow of electrons, and the electrons are flowing up into the cloud from the ground. And that's lightning. Now, lightning is very, very hot. So here is the lightning right here. It's about 50,000 degrees Fahrenheit. And that causes the air right around the lightning. And the lightning, the flow of electrons is about the size of my thumb. It's not big, but the flash and the heat is amazing. So the air right around that, it glows to 50,000 degrees and it expands. So anything that gets hot expands. As you probably know, things that get cooler, they contract. But the expansion of the air around a lightning bolt is so fast that it's faster than the speed of sound. And so thunder is a sonic boom. I don't know if you knew that or not, but thunder is a sonic boom. It's not because the lightning is hitting the ground and it's causing something. No, it is the expansion of the air so rapidly that it is faster than the speed of sound. It's just that simple. And that's an electrometeor. Also, let's see, what else do we have? We have another thing called photometeors. Let me erase this here. So got too much stuff going on. So we have photometeors, and a photometeor. By the way, St. Elmo's fire, which you can see sometimes off the tip of something pointy on an aircraft at high altitude. That would be an electrometeor. The aurora borealis would be considered an electrometeor. But a photometeor is like, anybody want to take a guess? You know, what would a photometeor be? Photometeor. Maybe you could get this. I don't know. Photometeor. A rainbow. A rainbow or a halo would be considered a photometeor. It's just caused by refraction of the light and something like that. So we have photometeors, we have electrometeors, we have lithometeors, we have hydrometeors, And the study of all these things in the atmosphere is called meteorology. I often wonder, why don't they just call it weatherology? Well, now you know, because we're looking and studying all of the individual elements that are in the atmosphere. The hydrometeors, the lithometeors, photometeors, and electrometeors. Okay. Now we have minor fog, and here it is. This is like ground fog or just mist. It's the BR. You've all seen BR. Like if visibility is 5 miles in BR, baby rain. It really, I just call it light fog is what it is. And we have special circumstances involving thunderstorms, lightning. This is a symbol for lightning. That means that you can see lightning but not hear thunder. That's possible. It could be far off into the distance. This is a precipitation that does not reach the ground. It's called virga. And then we have thunderstorm. So here's a thunderstorm, number 17, and that is you see lightning and you hear thunder. Okay. And when does a thunderstorm begin? You know, people would say, well, when warm air does this and it comes as a cold front and, you know, something happens there. No. Well, the thunderstorm begins when you hear thunder, and that's all there is to it. Now, the question is, when does a thunderstorm end? And a thunderstorm ends 15 minutes after the last thunder. 15 minutes after the last thunder. And you may not have known that. Probably not. Number 18 is the squall. Number 19 is the famous tornado. There it is. This is the symbol for a tornado. What does it look like? Kind of looks like the joining of the top and bottom. It looks like the atmosphere and the ground have come together. So that is a funnel cloud or a water spout or a tornado. Anything that happened that is not happening now but did within the past hour is called recent weather, and it has a little bracket around it. Those are all the 20s. Blowing lithometeors. Okay, so now you know what that is. You know what a lithometeor is, anything that is dry. So here we have, this is all blowing dust right there. Then we have blowing and drifting hydrometeors. This would be like blowing snow or blowing spray at the ocean front. The 40s are all fog, one type or another. We have regular fog, different versions of that. And then we have freezing fog over here, and that's the kind of fog that deposits rime icing. All of the 50s are drizzle, or well, most of the 50s are drizzle. We have a light drizzle, moderate, and heavy, and we'll get into what that means later. Then we have some freezing drizzle, and that is liquid that actually is falling through a below freezing environment. And as soon as the liquid touches literally anything, it freezes, which is very, very difficult because it just causes ice. Then we have a rain and drizzle mixed. Those are 58 and 59. Then we have the 60s. This is all rain. And again, we have light rain, moderate, and heavy. And you'll notice that there are two different versions there. I should tell you what that is. So there are three characters of precipitation. Characters of precipitation. You might think that all precipitation is the same. There are types of precipitation: rain, drizzle, snow. There are intensities: light, moderate, and heavy. But there are also characters, and so the first is called continuous. Continuous precipitation means that it just doesn't change much. It's raining at the same intensity and it just stays that way for a long period of time. So all of the 61, 63, and 65 are all continuous rain. Number 2 is intermittent. And intermittent precipitation, in this case 60, 62, and 64, that means that the precipitation slowly changes intensity. It becomes light becomes moderate slowly, then moderate becomes light. Maybe it stops and then starts up again. That's intermittent. And the third and final character of precipitation is showers or showery. And showers, remember, showers only come from one kind of cloud, cumulus clouds. Those are the clouds that are vertical. And the thing about showers is that because the clouds are so tall, they're not like widespread, they're tall, then the precipitation is very limited. It's just right under that area. And not only that, but the precipitation will start and stop very quickly. You can be on one side of the street and it is raining or hailing. The other side, there's nothing. That's due to the vertical nature of the precipitation, and those are called showers. So, once again, the three characters of precipitation are continuous, intermittent, and showers. You can have continuous rain, drizzle, snow. You can have intermittent rain, drizzle, snow. You can have rain showers. You cannot really have drizzle showers. Let me just tell you that. There are no showers of drizzle, but you can have showers of snow. Then we get to freezing rain, and this is probably the worst kind of weather of all. This is significant precipitation in the form of liquid that is coming down into an atmosphere. So it's warmer aloft, colder on the ground. It's like 25 degrees Fahrenheit on the ground, and all of that liquid hits the ground and immediately turns into a sheet of ice. That's worse than snow. I mean, you can't hardly even can't even walk, much less drive on it. So that is freezing rain. This is probably one of the worst kind. And of course, that's icing. Icing happens in the atmosphere at the higher elevations. It can happen. It happens with freezing rain, of course, on the ground. So freezing rain, and we have light, which is number 66, and number 67 is heavy, moderate or heavy freezing rain. Ay caramba, that's bad. Then we have liquid and frozen mixed, that is 68 and 69. Then we have all the frozen precipitation, and there's so many different kinds. There's light snow, moderate snow, and heavy snow. Then we have this thing which is called ice crystals, which is the only kind of precipitation that can fall from a clear sky. It only happens when temperatures are below or less than minus 22 Fahrenheit. So it has to be Arctic conditions, very, very cold. But it's very neat if you ever see ice crystals because, or sometimes they're called diamond dust or ice needles. And there's neat little visual, little photometeors that happen with it. You get these pillars of light. When I was in Alaska for many years, in the winter, sometimes I would see that, and I was in the Air Force at the time. And so, as you know, the aerodrome, the airport has all these different colored lights. There are red lights and green lights and blue lights, and there would be these little pillars of color above it, and it was really kind of cool. Then we have snow grains, we have snow pellets, we have ice pellets over here. So many different kinds of frozen precipitation. And then 80s, that's all about showers. You'll remember that. That is the type of precipitation. It is not a type. It is a character of precipitation that comes only from cumulus clouds. Even the symbol kind of tells you that it kind of comes right down. It's like a little yield sign, like it's pointing down to the ground. It's coming down to there. And so we can have light showers, we can have moderate or heavy showers. We have snow showers over here. So yeah, a snow shower would be that with a little snow sign above it. And we have hail. Hail is 87 to 90. And we have a whole system here of precipitation following a recent thunderstorm. So there has been a thunderstorm. You can tell by the little bracket down here, but it's raining right now. But it's not thundering right now. That was within the past hour. And finally, last but not least, is the thunderstorm in progress with other weather. And you'll notice the symbol for a thunderstorm is this, but if it is a severe thunderstorm, it is this. There's extra squiggles there, as in number 97 and number 99. Those are severe thunderstorms. I'm going to be also sending out a list of the 100 different kinds of weather. And you know what? That brings us to the end of today. We've already learned a lot about motion and meteors. So assignment number 1, and this will be due, let me just catch this. This will be due not this coming Sunday, but the following Sunday. We're going to be a total of 3 assignments, and the first 2 are due on the same day. It'll be at the halfway point. So you have 2 weeks for this. View the video that I sent out in the syllabus on the water cycle and water phase change. Read the FAA manual there, 80, 83, 28, chapters 11 and 13, and complete assignment 1. And here is assignment 1. So explain the water cycle in 1 page. Describe the 10 fundamental cloud types. You remember that? Those were the 10 genera. 2 pages for that. And then finally, generalize the 100 types of present weather. And when I say present weather, it's just what we talked about a moment ago, weather. And present a detailed description of weather types number 5, 18, 61, and the number correlating to the day of the month you were born. So if you were born on January 22nd, then tell me about weather type number 22. I've done this in the past, and people have thought they wanted me to know what the weather was like on the day they were born. So they go back through history, you know, whatever year that was. No, I don't want that. Just give me the weather that correlates with the date. Actually, I should say date probably that you were born. And that's it. And so next time, be here. It'll be on Wednesday. We will talk about stability and energy. And we've talked about a lot today, man. I'll tell you. Okay. So do any of you have any questions about anything? Yes, Daniel.
Wednesday, I will not be here. That's my scheduled flight block.
I think you told me that, didn't you?
No, I just now told you though.
Somebody. Okay, that's fine. This is all recorded, and so you can just take a look at that. And but if you are here, I'm always willing to interact. And whenever there's bad weather, especially there might be some severe weather in the east, you can always see how a meteorologist analyzes all that. It's all very good. All right, if there are no questions, then I will bring it to an end today. So thank you all. And if you want to watch this again, it should be available shortly as a VR. No other questions? All right. Oh, yes. Mitchell, did you have a question? Mitchell, raise your hand.
Yeah, I had a question about the, can you hear me okay?
About the what?
I had a question about the day of your birthday. Is that like, for example, I put it on the chat, like the 29th day will be the 29th weather symbol. Is that how you want it?
Yeah, you were born on the 29th?
Correct, 29th of December.
Sure. Oh, right before right before New Year's Day. Okay, so yeah, so weather type number 29, which I happen to just know is a thunderstorm within the past hour. Just, go ahead and just say that.
Got it.
All right.
Sounds good. Thank you.
Okay, Mitchell, where are you? Are you in Bakersfield or someplace else?
I'm here in Bakersfield.
Okay, very
Yeah.
good. All right, that's it. Thanks so much, everybody. Have a great day.
Thank you. Bye.
Bye.
Thank you, bud.